Hello everyone, let's go ahead and take a look at the intermediate value theorem. Now this is what the intermediate value theorem states. It says, suppose a function is continuous on the closed interval AB. If k is any real number such that f of a is less than or equal to k is less than or equal to f of b, then there exists a c that is also on the closed interval AB such that f of c is equal to k. Now let's go ahead and take a look visually at what that's trying to say. If I was to go ahead and say, here's where a and b are on my x-axis, notice that I'm going to have a closed interval there. And then I go ahead and substitute that particular a value into the function, and of course the function is going to give me a particular f of a value. Same thing with b. If I put b into my function, I'm going to come up with an f of b value. Now, I'm going to have to join these 2 points with a continuous function. So I've done here. I just went out like that, just went back up, and I made sure that this is a continuous function following those 3 particular conditions, and just joining the 2 endpoints there for my closed interval AB. Now, it says that k has to be any real number between the values of f of a and f of b. So it's going to be in between. So I just chose this value here, which is k. And then it says that there's going to exist a value c, and this is why we're going to be calling the IVT a continuity-based existence theorem. We're not looking for any particular value, but we want to show that there's something that exists. And there exists a c on AB, the closed interval AB, such that f of c is equal to k. So if this is what the k value is, if I go ahead and draw a horizontal line, then of course what has to happen is that there has to be an intersection of this horizontal line with the function itself. Now, in this particular case, there's actually 3 locations where that horizontal line and the function intersect. And when I go ahead and find those intersection points, I then go down to the x-axis. This is going to be my c sub 1, this is going to be my c sub 2, and this is going to be my c sub 3, because if I substitute those values of c into my function, it is actually going to be equal to the value of k. So that's basically what the intermediate value theorem is going to be doing for us. Now, here's an example of how we can go ahead and use the intermediate value theorem. Suppose we say that you have a function, x cubed plus x minus 3, and you just want to go ahead and prove that it has a 0 on 0, 2. Now, what I need to do, of course, is I need to go ahead and find out, first of all, what f of 0 is. F of 0 is going to be equal to negative 3. F of 2, on the other hand, is going to be equal to 7. When I'm taking a look at a 0, I'm basically trying to determine when f of x is actually equal to 0. And notice that that 0 is actually between negative 3 and 7. Okay, so what we have is we have all the pieces now to go ahead and use the intermediate value theorem to go ahead and show that there indeed is a 0 for this particular f of x on the closed interval between 0 and 2. Now, what we need to do, of course, as with any of these theorems that we have, is we need to go ahead and establish that the conditions are true. Once we establish that the conditions are true, then, of course, the result that follows will have to be true as well. Okay, it says that f of x is continuous on the closed interval from 0 to 2. Now, why is that true? Of course, if we go ahead and think about the 3 conditions that are needed for continuity, it will work for every point on this particular f of x. And the reason for it is because there, of course, are no points of discontinuity. There's no there's no domain restrictions. So we know that for any polynomial, you're going to have continuity so long as you have no points of discontinuity or domain restrictions on the interval that you're talking about. In addition to that, it says if k is any real number, such that f of a is less than k is less than or equal to b, of course, I have f of 0 being equal to negative 3. I want to have f of c being equal to 0, and we know that f of 2 is going to be equal to 7. So we know that k is going to be a real number that is between there. Therefore, what we know is that there exists a c that is on the interval, the closed interval from 0 to 2, such that f of c is equal to 0. And that's going to be a very good application there to ensure that we actually have a solution for this particular function without necessarily having to determine what that solution actually is. Okay, so there basically is an application of the intermediate value theorem. Now, there's a couple of other things that we want to take a look at as well, and it's about what is called bounded functions. Now, a bounded function, f of x, is bounded on a closed interval, again, ab, if for all x being on this closed interval from a to b, the absolute value of f of x is less than or equal to some m value for some m being an element of the real numbers. Okay, so we need to go ahead and also make sure that we remember that that symbol, that upside down a, means for all. Okay, so let's go ahead and take a look at here. Let's use this situation again. It says a function is bounded on the closed interval ab if for all x being an element of the closed interval ab, if I go ahead and take the absolute value of f of x, it is actually going to have a number m for which it is always under. Okay, the functional values are always going to be less than this particular value of m. Okay, and n has to, of course, be a real number. So if we go ahead and take a look at this particular situation here, here's a particular closed interval for all the x values that are here. Is it the case that if I take the absolute value of this function, there is going to be a number that it is always going to be less than or equal to? And for this particular case here, that value is actually f of b. Because if I go ahead and take a look at that as my highest range value, every other value of the function itself is going to be less than that. Okay, so that's what a bounded function means. Now, if we go ahead and take a look at this situation here, is this one bounded? Okay, now I'm going to go ahead and also say that we're talking about this closed interval here from a to b. Okay, a function f of x is bounded if for all x on here, the absolute value of f of x, okay, is going to be less than or equal to m for some real number m. Now, what we know is that for this particular function here, y is equal to 1 over x squared, there's going to be a vertical asymptote when x is equal to 0. And we know that if we take the limit as x approaches 0 from either the right or the left, we're going to come up with positive infinity. So notice that in this particular case here, this function would not be considered bounded. There is no m value such that we can say that all of the range values of this particular function is going to be less than or equal to that particular value. So in this particular case here, this would not be considered a bounded function on that particular closed interval. Now, let's go ahead and take a look at this though. It says if a function is continuous on a closed interval ab, then it is bounded on the closed interval ab. Now that's a pretty strong statement. Now, of course, when we go ahead and take a look at this one, it's obvious to see why this one is not working. And the reason for that is because, of course, we have a point of discontinuity. The function is not continuous, and therefore, it is not necessarily bounded. Now, in this particular case over here, though, if we go from a to b, notice that it's a continuous function, then we know that it is actually going to be bounded. Now, it is also going to follow that if a is less than b, and in this case a is less than b, then f of x has both a maximum and a minimum value on the closed interval ab. Now, because we don't have a be less than or equal to b, then that means that you're going to actually have differences in the values of the function, and therefore you're going to actually have a maximum value of the function and also a minimum value of the function. And if you go about playing around with a and b and try moving this someplace around here, because we know that this function is continuous, then you notice that there's always going to be a maximum and a minimum that's created. Okay, so just to go ahead and wrap up, we have the intermediate value theorem, which is a continuity-based existence theorem, we need to make sure that the conditions are true. If the conditions are true, then we know that the result will also be true. This is basically an image of what exactly is happening, and remember that you can actually have more than one C value on that particular interval. Then we went ahead and talked about bounded functions, and making sure that if a function on a closed interval has a largest range value, which is not infinity, then we can go ahead and say that that function is bounded. If the function is continuous, then we know for a fact that the function is bounded. And if those conditions are true and a is less than b, then we know that we're going to have a maximum and a minimum on the interval. Okay, so we'll go ahead and take a look at some of the problems that we have regarding this section the next time that we come together for class, and we'll take any questions that you have then as well. See you later. Bye-bye.